Okay. So I'm Daohan Wang, and I am a senior high schooler from Eleanor Roosevelt High School. And today I bring to you guys the low-cost 3D scanning system using a ToF imaging and Raspberry Pi, the solutions for young 3D studios. So let's jump right in. All right. So today the concepts we'll be going over is what is it, what does it solve, the challenges that we have faced during the production of the project, the experiments we have done, the limitations, and future improvements, and finally the closing. Let's continue. All right, so what is it? So 3D scanner is basically a simple tool that helps you to generate models that can be used in 3D modeling, design, video games, etc. And our core idea inside our project is that, so it is built on a Arducam Time-of-Flight camera, which captures depth map, a RP2040 microcontroller, which controls a motorized turntable, and a Raspberry Pi computer. And how it works is basically an object will be placed onto the turntable, and the Pi triggers the ToF camera to take a depth snapshot. And once the turntable rotates a few degrees, it will repeat that process until a full rotation is completed and generates a 3D model based on these captured images. As you can see, the science of that is basically going to be that after the depth map has been captured, we'll put them into a point clouds, and we go through a 3D mesh and using the Open 3D. And here's a picture of the 3D scanner we have built. So what does it solve? Well, the thing that inspired me to build this project was that I had lots of friends working inside rocketry, and sometimes they would use clay to mold like really weird and small objects. And trying to import these into the system, making it into a 3D model has always been really difficult. So it solves the difficulty in digitalizing real world objects, and it provides a portable device for young 3D hobbyists. Now the solution. So our 3D scanner was made with the Raspberry Pi 5 with the ToF camera and a motor, making it an accessible solution because the prototype cost a total of $150, and this is just the cost of the camera, the turntable, the motor, and the Raspberry Pi altogether. So compare that to the current other 3D scanner we have on the market. It is a lot more cheaper. As we can see down below, there are 3 current ones that we can buy directly from Amazon. Usually, most of them cost above $300, and we can see that the Scan Pro HD costs to $8,000 to $10,000, which I don't think any high schooler could be able to afford that. And when the product is might go into mass production, we think the cost of making one will be even less because we'll be buying the products in large quantities. And let's continue on. So the challenges we faced during the production of our project there was 3 major challenges. One was the sensor noise from the time-of-flight camera, which means that during scanning, there would be some errors that occurs with the scanning process. And the second was the synchronization between the camera and the turntable. Because the ToF camera is very sensible to disruption, such as like sudden movements and the shifts of the object onto the platform, we have to find a way where we can synchronize the camera with the turntable as it's turning and taking images synchronizingly. And there was also limited computing power on the Raspberry Pi because if those who know about the Raspberry Pi, it is a very small computer that only costs $65. So it can't really do very high operation calculation. So what are the things we did to counter these problems? So for the sensor noise, we did a collaboration routine where we use a reference object of a known dimension first before scanning so that the machine knows what it correlates to. And the second one of trying to make it synchronize more was that we use a micro stepping driver, which basically is making the rotation more smoother so that way there wasn't a lot more disruption than before. And lastly, for the high operation problem, we used a lightweight data pipeline. So where we converted each frame of the picture into a point cloud and stored into a compressed format. And the experiment. So our first experiment to show that the thing actually works was that we used the 50 millimeter times 50 millimeter times 50 millimeter cube, and we used 36 rotational steps. And so it was placed onto the 3D scanner, and it was repeated for 5 trials for consistency. And as a result was that we got a mean sighting of 49.95 millimeters and an error range of 0.7%. As we can see, the error range is less than 1% and basically shows that it has the capability of generating a very accurate model of the thing that was supposed to be scanned. And later on, we tested also the device in different kind of working conditions in the office, because usually the thing where we think that you'll be using this device will be inside like office or schools. So basically the test was run under 3 different lighting levels where we have low light, office light, and bright light. And the result was that the project works best in the low light and office light, and it has the largest area inside the bright light. All right, and here is a video demo of the project as, oh shoot. So as you can see, the bottom is the code running. That was the cylindrical object used during the light project. And you can see as the turntable is turning around, we can see that the code is taking frames of different pictures and storing them into a mesh cloud. And the STL model you see in your upper left corner, I believe, is the model that we generated using the camera. And down below is the model itself that was used to 3D print the cylindrical object. So some limitations on our device was that, so first of all, it doesn't work in high lighting conditions, and it can only scan objects that fits onto a turntable. And it also cannot scan very super small objects that are very detailed, like let's say like a Lego brick. And the sensor noise still exists because there wasn't really a best way where we can make the time-of-flight camera better itself. So that is something we have to improve on into the future. So since we're talking about the future, let's talk about the future development of our project. So first of all, we wish to make the device a little bit more portable because bringing a huge, gigantic turntable around with a separate piece of the camera would be somewhat difficult. And we wish to have more precise modeling, maybe switch out the ToF camera perhaps, and also a feedback loops on the turntable because we wanted to, for the project to be as precise as possible, we want the turntable to have a feedback loop on itself. So that way, if it detects any mistake, it can turn back to that angle and retake that frame in order to correct it. And we also wish to implement AI for model predictions because sometimes there's still going to be disruption that exists, maybe like sudden vibrations, sudden movements, and maybe the feedback loop isn't enough to fix that. So we wish to implement some sort of AI algorithms so that it can predict what the device we are scanning. And the most important thing is that we wish for a better algorithm at generating the mesh cloud where we have smaller details but faster speed. So this is my contact information. If you do show interest into providing more affordable devices for young enthusiasts, please contact me and we can work together. Thank you, and that will be all. Any questions?